Okay, so let us continue our discussion on Z transforms. We have the definition of Z transforms in front of us. It is given as summation n is equal to 0 to infinity y n t z to the power minus n. In the previous lecture, we saw how to perform Z transformation for some standard functions, including a constant function and an exponential function. Let us see how we can actually make use of this concept. Before we make use of this concept, let us try to solve an analogous problem in Laplace transform, so as to lay down the steps, and then we would like to repeat the steps for Z transform. So, this is a Laplace transform in front of you, and you would like to invert the Laplace transform. Okay. So, you would like to obtain y of s, now y of t, right. So, what you have here is y bar of s, which is equal to s squared minus s minus 6 divided by s cube minus 2s squared minus s plus 2. So, when you want to determine the inverse Laplace transform so as to determine y of t, the first thing which you want to do is to factorize the denominator. Okay. So, here in the denominator you have s cube minus 2s squared minus s plus 2. I have already factorized this for you. So, what you should get is s squared minus s minus 6 divided by s minus 1 s minus 2 s plus 1. Okay, let me check if this is what we get, s minus 1 s minus 2 s plus 1, right. So, what was the next step that we generally follow? So, this is what you have for y bar of s. And the next step that we do is we determine the we split this as partial fractions, and for that let me say that I have s squared minus s minus 6 divided by s minus 1 s minus 2 s plus 1 is equal to a upon s minus 1 plus b upon s minus 2 plus c upon s plus 1. Okay. So, I assume that it is possible to split this particular expression in as a summation of 3 individual expressions, a upon s minus 1 plus b upon s minus 2 plus c upon s minus 1, from where I get a multiplied by s minus 2 s minus s plus 1 plus b multiplied by s minus 1 s plus 1 plus c multiplied by s minus 1 s minus 2 is equal to s squared minus s minus 6. Now, what is the next step? The next step is that in one step I will assume s is equal to 1, from where I would get rid of b and c, and I will simply substitute s is equal to 1, I will get the value for a. In this next step I will substitute s is equal to 2. So, I will get rid of a and c, I will get the value of b, and in the final step I will substitute s is equal to minus 1, and in that way I will get rid of a and b, and I will get a value for c. I have already done that. So, I have in front of me y bar of s after doing this partial fraction, y bar of s is equal to what? Let me write this. This is equal to 3 upon s minus 1 plus minus 4 by 3 s minus 2 plus minus 2 by 3 s plus 1. Okay. And then let me try to understand why I bother to do all of these things. I did these things because I know that now each of these individual expressions are in a standard form such that I can go back and do the inverse Laplace transformation. I know that function which when applied with Laplace transform would give me this expression. That is the way to do the inversion of Laplace. So, therefore, I know that this would be equal to y of t. I would do an inversion on both the sides, and the way I get 3 upon s minus 1 is if I do a Laplace transform of e to the power t. Okay. If I do Laplace transform of e to the power t, I will get 1 upon s minus 1. So, 3 upon s minus 1, the Laplace inverse Laplace would be 3 to the power t. Similarly, minus 4 over 3 e to the power 2 t minus 2 by 3 e to the power minus t. Okay. So, this is the inverted Laplace of y of s, y bar of s is equal to s squared minus x minus 3 divided by s cube minus 2 s squared minus s plus 2. Okay. So, this is what I get. The steps were very clear. You factorize the denominator, do a partial fraction, do the inverse Laplace of individual terms, right. So, now can I make use of this procedure to get the inverse Z transform if I already have a Z transform? Let us see if this is possible. So, what I have here in front of me is a Z transform which is given as this. Okay. So, the Z transform here is this y hat of Z is equal to Z upon Z squared minus 4 s plus 3. Very similar to the Laplace transform, I also have something in the polynomial in the numerator, a polynomial in the denominator. So, I would like to do a factorization of the denominator, except that before I do that I make a small change. The change which I make is this: y hat of z is equal to, I look at the denominator, I will determine the highest power in the denominator and I divide it by the highest power in the numerator and the denominator. So, in the denominator the highest power is 2. So, I will divide the numerator and the denominator by z squared, which will give me z inverse upon 1 minus, so this has to be z, for z inverse plus 3 z inverse squared. Fine. Now, I will try to do a factorization. Everything is in terms of inverse, it is a little inconvenient to see that. So, for the time being I will make a ad hoc substitution, and I will say that let z inverse is equal to x. So, what would happen? I can write 1 minus 4 z inverse plus 3 z inverse squared would be equal to 1 minus 4 x plus 3 x squared. Now, I would like to do the factorization. So, I have in front of me 3 x squared minus 4 x plus 1, this should be equal to 3 x squared minus 3 x minus x plus 1, this should be equal to 3 x minus 1 minus 1 x minus 1, which is equal to 3 x minus 1 x minus 1. Right. So, I have done a factorization, and now I would like to use this fact for determining the factorization of the denominator. So, let us see how I can do this. So, 1 minus 4 z inverse plus 3 z inverse squared. Let us see. I have x minus 1. So, 1 is a root. So, therefore, I can write this as 1 minus z inverse, because everything is inverted. Similarly, I have 3 x minus 1. So, 1 over 3 is a root. So, therefore, I can write this as 1 minus 3 z inverse. Okay. And let me see if this inversion makes sense. I used the last expression 3 x minus 1 x minus 1 to write this. How did I do that? I looked at the zeros. 0 for x is equal to 1 over 3. So, I inverted it. So, the corresponding term will become 1 minus 3 z inverse, x minus 1 is equal to 0, 0 is 1. So, the corresponding term will become 1 minus z inverse. So, 1 minus 4 z inverse plus 3 z inverse squared, correct. So, therefore, I have now factorized. I have first thing which I did was I divided the numerator as well as the denominator by the highest term, the term with the highest power in the denominator. Then I factorized the denominator. So, y hat z is equal to what? Z inverse upon 1 minus z inverse 1 minus 3 z inverse. So, what is the next step which I should do? Analogous step, I should do a partial fraction. Okay. So, I have already done the partial fraction for you, and the partial fraction which you should get after doing this correctly. Remember, what you would do is you would make it as a upon 1 minus z inverse plus b upon 1 minus 3 z inverse, multiply cross multiplication, invert it to z inverse, you should get the value of a b, trivial. So, what you should get is this minus 1 upon 2 1 minus 1 minus z inverse plus 1 upon 2 1 upon 3 1 minus 1 minus 3 z inverse. From where I can write y of t, in fact y of n t. It is very important that you do not get y of t here, because we are dealing with discrete time systems. We get y of n t at specific locations of n as inverse z transformation of minus 1 over 2 1 upon 1 minus z inverse. Since z transformation is a linear transformation, I can further write inverse Z transformation of 1 over 2 1 upon 1 minus 3 Z inverse, right. So, now I have converted my relatively complex expression into simpler ones, and does this look familiar? Well, this is simply a Z transform of a unit constant function, right, because if we remember Z transformation of a constant function was what? C times 1 upon 1 minus Z inverse, right, from where I can get the inverse Laplace transform of 1 upon 1 minus Z inverse is simply unity, right. So, therefore, what I can write here is y of n t is equal to what? Minus 1 upon 2 plus inverse Laplace Z transformation of 1 over 2 1 upon 1 minus 3 Z inverse. I still need to do inversion of Z transformation of the second term. First term is pretty straightforward. So, let us see how do I get the inverse of the second term. So, I have this, what I need to do is inverse Laplace transform of 1 upon 2 1 upon 1 plus or minus 1 minus minus 3 Z inverse. How do I do this? So, let me simplify this. This will simply become 1 over 2 Laplace Z inverse of Z upon Z minus 3, right. I have simplified that expression, and does this look any similar to what I have obtained previously? So, let us see. I have the Z transform of e to the power minus a t is equal to what? Z upon Z minus e to the power a t, right. This is what we got previously. Please refer to the previous lecture, you would see this. So, therefore, Z inverse of Z upon e upon Z minus e to the power a t would be what? It would be e to the power minus a at 0, e to the power minus a at t, e to the power minus a at 2 t, and so on, right. Remember that we are doing the analysis in discrete domain. So, therefore, you do not get a function, you get a series of values. So, therefore, what will happen? Z inverse of 1 over 2 1 upon 1 minus 3 Z inverse would be what? 1 upon 2 e to the power. Now, here you need to look and compare this. You have this term e to the power a t, and here you have 3, right, which means e to the power a t should be equal to 3, okay, or a capital T should be equal to ln 3 log of 3, which we know that it is very close to 1.1, very close to 1.1, right. So, therefore, what would happen here? This would be half this would be half 1.1, but now you have discrete values, you have values at n is equal to 0, n is equal to 1, n is equal to 2, and because you are sampling at every t, right. So, this would be multiplied by n, okay. This would be multiplied by n, except that, so this is e to the power t. So, I have e to the power minus a t, the value of a t is this. So, it should be e to the power 1.1. So, this is your inversion. So, let me repeat the steps very quickly. You need to determine the inverse Laplace of 1 over 2 multiplied by 1 over 1 minus 3 z inverse, half was taken out. So, z inverse of z upon z minus 3, you compared it against the Laplace the z transform of e to the power a t, and that was z upon z minus e to the power a t, from where you found that e to the power a t must be equal to 3 for the present case, which means a t should be equal to 1.1. Okay. So, therefore, you have e to the power a t, where one more correction should be yeah, that is correct. So, you have e to the power minus a t, and you have determined the value of a t as 1.1. So, when you do an inversion, what you should get is half, which is already come out, e to the power a t, okay, and this should be equal to 1.1 times n, where n is an index. So, n belongs to 0, 1, 2 and so on. Okay. Finally, let us check whether we did any mistake in the sign. The Laplace transform of e to the power minus a t, okay, fine, this is the one. So, this is the Laplace transform for the second factor that you get. So, therefore, what you should have is that y of n capital T, y of n capital T, okay. What we got from the first term minus 1 by 2 as it is, right, minus 1 by 2, yeah, plus 1 by 2, and then for the second term which we got was e to the power 1.1 n, where n is 0, 1, 2 and so on. This is the inverse Z transform of the Z transform, which has been given as equation number 3. Okay. So, let us relook into what we did. We looked into the solution procedure of Laplace transform, factorized the denominator, simplified into simple ones, inverted it to get the y of t. In case of Z transforms, the first thing which we did was divided the numerator and denominator by the highest power of z, then factorized the denominator, did the partial fraction, inverted it. Except that you have to understand one thing, that you cannot get a function back, you will get after z inversion the values of the function at discrete points of time. So, therefore, your as you can see on the screen, the inverted Z transform has n. So, at discrete intervals of time you will get different values of n. So, we will stop here today, and then in the next week we will continue our discussion on how to use Z transformation for the analysis of dynamical response of discrete time systems. Till then, goodbye.